This video is about conic sections, specifically hyperbolas. For our notes, we'll understand the general algebraic definition of a hyperbola. There are a couple different options, and there's a lot of clutter with these definitions. We'll try to lay it out clearly here. The graph of each of the following equations is a hyperbola with center at the origin. Okay, so again, that's our scope. We're talking about the origin as the center for these, and having the given properties. Now, there are two different options for the way you can write the equation. I'll try to compare and contrast them side by side as we go. The first option could be considered as the x squared over a squared minus y squared over b squared equals 1. You'll notice a couple things. First of all, it looks a lot like the ellipse equation we just discussed, but you'll notice there's a minus sign. That's actually the giveaway about whether an equation like this is an ellipse or a hyperbola. So in a hyperbola, you will see a minus sign there, and that's key. Also notice that a and b are both positive, and so we're not talking about a or b being larger than the other as we would consider what the ellipse forms. Rather, in this case, as we'll see soon, it's not about which one's larger, but about which one is in the first term, or the positive term. Now the vertices are plus or minus a comma 0, and then there's a transverse axis. Okay, so these are key aspects that will come out when we start graphing things. We have vertices, transverse axis, and then asymptotes. And the way that we graph them will actually lay those characteristics out nicely for us. So we won't necessarily have to panic about having to memorize all these things. Though, if that's your style, if you just want to look at this chart and strictly memorize it, that's fine. But I think there's a more flowing way to get it all going. Once we do an example, you'll see it. Also, we have foci, just like we did with an ellipse and a parabola actually, but foci are plus or minus c comma 0. This time, the equation that relates a, b, and c is different. It's c squared equals a squared plus b squared. You'll notice that's different. The ellipse had a minus in its equation of the same type. Okay, and then the visual of a hyperbola is actually that of two parabolas that are kind of opening away from each other. You'll notice in the visual sense that for the graph, you have this thing called the transverse axis. That is the axis that actually hits the parabola branches. So in our first example, where the x squared variable was first, let's tie this all together. If the x squared variable is first, then the transverse axis is horizontal. That goes along with the x variable. And the picture has branches that intersect on the x-axis. And in other words, that's where the vertices actually hit, on that axis. Of course, the foci are just like they were with parabolas. They're being hugged by these two branches. If we consider the other option, notice it's very similar. This option reads y squared over a squared minus x squared over b squared equals 1. So notice there's the minus sign there. Again, that's a key observation for knowing if it's a hyperbola. But notice this time, the y variable comes first. Now, if I can trace that back through all these characteristics like we just did for the previous setup, notice when the y variable is first, your transverse axis is vertical. That goes with the y variable. And notice that in the graph of this thing, there are two branches, two parabolas, and they would intersect the y-axis. That's where the vertices are. Okay, and then these asymptotes, those will come to life as we start to graph these. You'll see that they're not that complicated. In fact, they're simply these dashed lines that are connecting opposite corners of this strange box that's in the middle of the graph. So we'll understand that characteristic, I think, easily when we start to graph these. Speaking of graphing a hyperbola, let's talk about how to sketch a hyperbola. There are several key steps. First, we're going to sketch the central box. That's that strange dashed box we saw kind of floating in the middle of our two examples of hyperbolas above. So we'll understand how to graph that with an example. This is the rectangle centered at the origin with sides parallel to the axes. Okay, so we've seen that. The dimensions of this box will come directly from the equation, as we'll see in our example. Okay, and then secondly, once we get the box sketched, we're going to sketch the asymptotes. Remember, these will just connect the corners of the box, so you could call them the diagonals of that central box. And then thirdly, we're going to plot the vertices. Part of, or two places on the box will actually get some points, and those will either be the x-intercepts or y-intercepts for cases centered at the origin like these. And then lastly, we're going to sketch the hyperbola, which is really just two kind of parabola-looking branches that go away from each other, and they're kind of bound by all the characteristics that would have already been plotted by getting to this step. Let's consider an example where for the following equation of a hyperbola, we want to do two things. First of all, find the vertices, foci, and asymptotes, and then secondly, graph it. Now this all kind of runs together, so I think we'll see it that way. When we look at our first equation, it reads x squared over 9 minus y squared over 64 equals 1. Now you'll recall from our steps above, the first step is to try to get this box plotted on our graph. Now this first variable gets the points. That's a summary of many of the characteristics in our big long description above with all the formulas in it, okay? The first variable gets the points. So this is a simple way to know how to graph it. If x is my first variable, as it is in this case, then I go square root of 9, the number under the x squared. Okay, that happens to be 3. I go that direction left and right, and I put actual points there because the first variable gets the points. So I have points plotted at 3, 0 and negative 3, 0. Okay, now what does that mean for y? Well, we move on to the next variable. Underneath the y squared, we find a 64. So we go the square root of that amount, you guessed it, above and below our center. But here, we're not going to put points because, again, the first variable already got the points. So what do? Well, the square root of 64 is 8, so I'm going to go 8 up and down. That'll take me a little bit off my grid. And I'm just going to put some tick marks there, not actual points, okay? Because we're just going to use these to get the dimension of our box. If I now connect a box with the dimensions that span as high and low as those tick marks I put, and as left and right as the points I put, we're making this a dashed box. And just do your best to try to graph it accordingly. Okay, we get this phantom dashed central box showing up. That's the first step in understanding how this parabola will be drawn. Now, most importantly in the box is its corner coordinates or vertices. So I'm going to go ahead and kind of darken those in. I need to be able to trace them easily. And again, hand-drawn pictures aren't the best, but it's as good as we have right now. So there's our phantom box. Now, once you get the box drawn, recall, there are only points on two sides of it. They happen to be on the left and right side, as we said earlier, because the x variable was first. The top and bottom of this rectangle do not have points. Those are just dimension holders for the box as far as how high and low it goes. Once we get this box plotted carefully and all the corners clearly labeled, we're simply going to connect the opposite corners of the box to form some asymptotes. Now these are kind of hard to draw perfectly by hand. You may want to use some kind of straight edge or something. But we have a crisscross X looking design of some asymptotes, which I've drawn as dotted lines here. And that's exactly how they should show up according to what our definition said above. Once we get those asymptotes plotted, we can go ahead and just draw the two branches of the parabola. Here's the trick. They have to intersect the points we drew. Remember, those points were only left and right. So we're going to draw two kind of wide opening parabola looking branches that are kind of bound by the asymptotes and the box. So it's kind of using all the stuff we already have on here as the boundaries. And that's our hyperbola. It's those two branches put together. Now everything else we've drawn, such as the box and asymptotes, those are essential pieces to getting the hyperbola drawn. They're not actually the hyperbola, but they're part of the graph because of how important they are. Speaking of the asymptotes, let's also understand that they have some nice simple equations, especially when centered at the origin, as this hyperbola is. These are just lines, and remember, lines are just y equals mx plus b, except b is 0 if they both intersect the origin. So we could just say y equals mx for these asymptote equations. There's no b to put in there. And then you can understand the slope of them to be rise over run, which is actually already spelled out for us in the dimensions of this box. So notice the rise, if you were to count the vertical distance of the entire rectangle box, Remember, we made that box by going up and down 8 from the original 64 value underneath the y squared, which means that this entire rise would be 16, and then the entire run going all the way across horizontally with the dimensions of the box, we went, remember, 3 right and 3 left, so that full horizontal dimension would be 6. And so if the box is 16 high and 6 wide, then rise over run for these lines would be plus or minus, right? So plus or minus is because you have one going upward and one going downward, left to right. They're both otherwise the same equation. The rise would be 16 and the run would be 6. Of course, we can reduce that so that the equations of these asymptotes would simply be plus or minus 8/3. Those are just linear equations of the asymptotes, and that's exactly what we have graphed. Now let's also go back. We haven't quite plotted the foci for this graphing example, so we're going to go back and work on that a little bit. If you recall above, the equation to get this would be c squared equals a squared plus b squared. It's different than it was for the ellipse. If you go back to our notes, you'll recall that equation showed up in actually both cases the same, c squared equals a squared plus b squared. So we already know a and b from our equation. Remember, a squared is the first denominator, in this case the positive one for a hyperbola, and of course b squared is the second. So in this example we have c squared equals a squared was 9 plus b squared was 64. We're just adding these up, so we can say c squared equals 73, which means c equals the square root of 73. Remember, we don't need a plus or minus for this. We have positive distances here. This is approximately 8.5. That'll just kind of help guide our graphing. Remember, the foci for a hyperbola are being hugged by its branches. So if I go 8.5 units, which will actually be a little off our graph, there's focus 1, and then 8.5 units, again off the graph a little bit on the right, that's focus 2. That's where the foci would occur for this parabola. So now we can say we have the vertices plotted, we have the foci plotted, we have the asymptotes plotted, and we even have the equations of the asymptotes and the actual locations of all of these other characteristics. Let's try another example where for the following equation of a hyperbola we want to do a couple things. First of all, find the vertices, foci, and asymptotes, and secondly, graph it. Now this equation reads 25y squared minus 9x squared equals 225. You'll make an observation hopefully right away that this does not quite line up with the general form of a hyperbola listed above in our notes. Namely, we need this number on the right side to be a 1, and it's not, but we've seen this before. We can easily make that a 1 if we divide everything by what that number is, which is 225. So if I divide by 225 all the way across, I'll have to just reduce these fractions. I'll end up with a y squared over 9 minus an x squared over 25 equals 1. And so now we have what we need for this. Notice in this equation the y variable is first. That means that axis gets the points. The first one gets the points. So the y-axis, vertically speaking, then will go up 3 and down 3, the square root of 9, from the origin, which is where our graph is centered. If we go up 3 and down 3 and put some points, we're going to call those the vertices. Now remember, we have to use the other variable to get the dimensions of the box. So underneath the x squared variable, we have 25. That means we're going to go right 5 and left 5, but when we get there, we're only going to put tick marks, not an actual point. And then we use these dimensions to sketch a box so it goes as high and low as the points in this case, and as left and right as those tick marks. And once we get that sketched, we want to connect its vertices to get some asymptotes. Once we get the asymptotes drawn, notice they crisscross. That's what they should be doing as diagonals of a rectangle. And we now just recall where our points are. Remember, the points were above and below on the y-axis. We simply now draw two branches of the hyperbola that are kind of bound by all the stuff. So they're bound by the asymptotes, and they intersect the vertices that we've drawn high and low, which means these two branches of our hyperbola will be opening upward and then downward, kind of running away from each other. Okay, so we've done several things. We found the vertices. Now the foci we still have to find. Remember, for the foci, this is the c squared equals a squared plus b squared formula. And we know these numbers, so c squared is going to be just the sum of these two numbers in the denominators. That's the a squared and b squared. Well, that's 9 plus 25, which is 34, which means c is the square root of 34, which is approximately 5.8. And so we'll go ahead and plot the foci using this value by going up and down 5.8. Remember that the branches of the hyperbola should be hugging the foci. So we have one above and one below in their places. Of course, you could write their coordinates if you needed to. It'd be the point 0, comma, square root of 34, or 0, comma, negative square root of 34 for the foci. And that's now covering the foci, and then the asymptotes we already graphed. We can get their equations by recalling that it's going to be y equals mx, where m is the slope of the lines. But if you count just the dimensions of this box, the rise would be a 6, and the run all the way across would be 10. And so if you use a slope of rise over run, then we have 6 over 10. Of course, it should be plus or minus because there are two of them in opposite directions, which means y equals plus or minus 3/5 if we reduce that x. Don't forget the x there. Let's try another example where for the following equation of a hyperbola, we're going to do two things. The usual, we're going to find the vertices, foci, and asymptotes, and then we're going to graph it. Now this equation is given as x squared minus 3y squared plus 12 equals 0. Well, at first glance, you'll observe, I think, that this is not in the standard form that we have defined above in our notes, which means we have a little bit of work to do on it. We'll start by subtracting 12 from both sides. Now, this may not seem like the obvious good thing to do, but just hold on, let's see what happens here. So I'll have x squared minus 3y squared equals negative 12. Recall that we want this in general form for a hyperbola to be equal to 1, which means we're going to have to work on this to get that. We've done this already where you can just divide by the number you have over there that's not 1. So if I divide by negative 12, of course, I'll have to do that all the way across. Okay, let's see what happens. I'll end up with negative x squared over 12. And then notice I had a minus between the terms, but now I'm dividing by a negative, so now it's going to be a plus. And then it was 3 over 12, so I could just call that y squared over 4 by reducing it, and then that equals 1. Okay, what we have is looking better. At least it's equal to 1. But it strangely has this negative sign just kind of flapping in the wind out in front, which we don't want. Furthermore, now there's a plus between the terms. And so what's going on? Well, we can spot this as a hyperbola if we do one quick little fix, and that is simply just switching the order of these terms. So I could write this as y squared over 4, and then minus x squared over 12 equals 1. Just simply switching the terms and bringing the signs with the terms, which is always appropriate. It puts it automatically in a general hyperbola form, which is exactly what we'd like. Now let's understand a couple things. First of all, the y variable is first, which means that variable gets the points, or that axis gets the points. So to give the vertical axis, the y-axis, the points, I'm going to start from my center 0, 0, and go up and down the square root of the number under it, which is a 4. So I'm going to go up 2 and down 2 vertically and put some points at those places. Of course, these are going to end up being my vertices. Those are the points 0, 2 and 0, negative 2. And then left and right, we're going to have to go the square root of 12. Let's just note that the square root of 12 is approximately 3.5. We may want to use the exact value, of course, when we're expressing it, but for the sake of graphing it, we're going to have to estimate with a 3.5. So we're going to go 3.5 left and right, but then when we get there, remember, we're not putting points here. We're just holding this to get the dimensions of the box we're about to draw. So then we'll go ahead and draw a box that contains, or that involves the dimensions as far and left and right as the 3.5 value, and as far as high and low as our point values, plus and minus 2. We'll go ahead and draw some slanted asymptotes connecting the corners of this box. Once we get those in there, we're pretty much set to go because we have the vertices already plotted, which means we know exactly where to draw the branches. These branches will be opening either upward or downward to connect and use those vertices that we've already drawn. And so there's the graph of our hyperbola. Now let's also get the foci graphed. Remember, for the equation of the foci, we can use c squared equals a squared plus b squared. That means c squared equals, in this case, all the way down where we kind of ended up, a and b were, a squared and b squared rather, were 4 and 12. So that means c squared is 16. Oh, finally a nice number, which would mean that c is 4. Remember, we ignore the plus or minus in the case of distances here. So that means I'm just going to go 4 units on the major axis, on the transverse axis, which is the one that has the vertices. I'm going to go 4 units high and low and put 2 points there as the foci. So there's a focus at 0, 4, and there's a focus at 0, -4. So now we have the vertices graphed and labeled. We have the foci graphed. For the equations of the asymptotes, again, we'll just look at the box and determine its dimensions. It went as high and low as above 2 and below 2. So we'll say the vertical rise of the box is 4. And then the run of the box, of course, this was the nasty number. Remember, we went square root of 12 in either direction. So if you double that, you would get 2 square root of 12. Of course, you can even reduce that. That would be 2 times, the square root of 12 is really the square root of 4 times 3, so that's really 2 root 3, which is really 4 root 3. That's the dimension of that box. So for our slope of the asymptotes, we'll say we have y equals plus or minus. The rise is 4 over the run is 4 root 3, and then x for our variable. But then the 4's would cancel, so we could say y equals plus or minus, and then it's 1 over root 3. You could rationalize it to be root 3 over 3 if desired. You wouldn't have to, but you could. So really the equation of the asymptotes is y equals plus or minus root 3 over 3x. Let's try another example where this time we want to find the equation of the following hyperbola, which is graphed for us. Now we can understand the characteristics of this graph and try to pack them into the formula as we know by now. As labeled on this graph, we have a couple things. First of all, it's opening upward and downward. Immediately that should tell us a couple things. Let's go ahead and get our equation set up. Remember, it's a subtraction between 2 fractions, supposed to be equal to 1. And if the vertices for this graph, which are shown, are on the y-axis, remember the y variable should come as the first one in the first term. So I'm going to put y squared on top of the first fraction, which automatically means x squared should be on top of the second fraction. And then underneath the y squared, think about what we would expect to find here. We're expecting that to be the square of the distance above and below the center, which is at the origin, on which these vertices lie. Well, the vertices are labeled as the points 0, 12 and 0, -12. And so if I square that number 12, that means 144 would be the number underneath the y variable. That's the transverse axis. And so that's the square of that number, the distance from the center to those vertices. And then for the x value, remember, we don't know this exactly, but what we do know is that c squared equals a squared plus b squared, and we are expecting to find b squared to be the value underneath the x squared. Furthermore, it's also given that the foci coordinates are 0, 13 and 0, -13. Well, that's giving us actually a lot of information. That tells us that c squared would be 169. That's the coordinate of the foci, the y coordinate squared. So 169 would be our c squared value. Okay, that means 169 equals a squared, which we already found to be 144, plus b squared, which means we can solve for b squared. This would simply tell us that b squared equals 25. So automatically then we can just throw that number up in its place and write, instead of b squared, a 25 underneath the x squared. And that accounts for the foci, which we had to use to find the b value. It accounts for the vertices, which we had to use to find the a value, which means this is our final form of our hyperbola. It's y squared over 144 minus x squared over 25 equals 1.